Thank you so much, everyone. I'm thrilled to be here today to perform for you something I call Buzzkill. Funnily enough, my nickname in high school. So I'm Justin. I'm the Director of Research and the self-appointed social media mogul at Tanto Security. We're a research-driven offensive security services firm based in Australia. There's a couple things I love in life. One of them is making a short story long. We're in for a hell of a ride today. The other is making computers weird. My background is in software security, so I love bugs, vulns, and exploitation. But more than this, I love making the bad guy's computer weird. And this started for me with the Wi-Fi Pineapple, which is this little Wi-Fi network pen testing device that a lot of people pick up at the Hack 5 booth at DEF CON. Some people are so excited to have their very own Wi-Fi Pineapple that they turn it on and walk around jacking up everyone else's Wi-Fi, which is hilarious, especially in 2015, when someone is walking around automatically compromising everyone's Wi-Fi Pineapple. They were soft-bricking them and defacing them with a message that said, if you want to get this back up and running, you'll have to work out how to restore the firmware yourself. Good luck and have fun. This was some performance art by Dr. Wes McGrew, who went on to do a few years' worth of presentations all about pen tester security. He made the case that pen tester tools can have bugs too, demonstrably, and certain processes that pen testers perform can have risk. Furthermore, pen testers are the kind of people with access to really, really interesting client data, things like credentials and pen test reports, which is like a how-to hack for their customers. And pen tester laptops travel into really interesting places. It's a good spot to hitch a ride. Following on, there's a couple of things that I think are relevant. In 2016, the makers of Cobalt Strike, the very popular red team tool / cybercrime tool, depending on your point of view, said that the team server, the C2 component of Cobalt Strike, was being exploited in the wild through a vulnerability. And in the summer of 2021, you weren't cool as a security researcher if you weren't getting DMs from North Korea with malicious Visual Studio projects. So I fell in love with this idea of finding vulnerabilities and hacking hacker tools. Some of the bugs I'm most proud to have found in my career were in Metasploit itself, which is hilarious because there's now modules in Metasploit for exploiting Metasploit. Like the name finally makes sense to me now. Now we're going to have a lot of fun today. I take that back. I'm going to have a lot of fun today. But I need you to know I love and respect software developers. This whole shtick that hackers have about software developers is stupid. Like, that needs to stop. That's hurtful, and it's not good. I mean no disrespect at all to the makers of what we're going to talk about today, and I don't just say that because they're in the room with us today. They've come all the way from the US to see this talk and to see your beautiful country for the next couple of weeks. So if you see the tech romancer around, please make sure you make them feel welcome. I'm not sure I'm doing a very good job of it up here. But what I want to get across is the tools that we use can have bugs too, and the way we conduct ourselves as professionals, we have the responsibility to keep ourselves safe and our clients safe. So I want to talk about Bbot, which is an open source attack surface mapping tool. So what it does is it's very popular among pen testers and bug bounty folks. It's really good at kind of mapping out the surface of an organization. The user of Bbot can point it somewhere like Tesla.com and send it on its way, and it'll find all the various attack surfaces belonging to that company. Internally, it's built on modules and events. It's a modular kind of plug-in based system. So these modules will listen to these things called events, which contain attack surface information about the thing it's exploring. This can be things like DNS host names, IP addresses, URLs, passwords, and vulnerabilities. It'll think about what it's seeing in these events, and it'll go and perform its own attack surface mapping, advertising what it finds onto the message bus for other modules to pick up, for it to do its own thing, to put stuff on the message bus. Some of these events can loop back around, and you get this beautiful bouquet of attack surface mapping findings. Bbot ships with 91 modules and 32 different event types that it can raise. And I wanted to zoom in on these modules when someone dropped a Bbot in the work chat early this year, for a couple of reasons. I figured it was probably the area of the code base that had been touched by the most number of people, had the most diverse set of authors. And if my examination of the Git history is correct, which it probably isn't, but it's probably directionally correct, it's far and above the most frequently, or not most frequently touched area of the code base, the area of the code base with the most distinct authors. And as well as that, modules are on the cold face of reaching out over the internet, touching untrustworthy hosts, pulling data back, parsing it, and trying to make sense of it. It's a good place for bugs to lie, because I don't know if you've used the internet lately, but there's some pretty awful hosts out there. So I took it upon myself to audit all 91 modules of Bbot, and I'm thrilled to be able to share the results of that with you today. We'll cover it in 3 sections. We'll start with archive extraction, then we'll talk about Git repo pillaging, and close with some discussion about the leakage of Bbot user API keys. All these bugs are fixed, so if you run Bbot, go patch your Bbots. Otherwise, I hope you enjoy these stories. So to start with, archive extraction. I love archive extraction. It's a place where this certain type of bug class can live, known as like directory traversal or arbitrary file write. And this is by no means a new type of bug. As far as I can tell, it goes back to at least 1991. Like there was an article in Frack that talks about exploiting the World War IV BBS software using pkzip. Throughout the 2000s, almost no unarchiver went untouched by this type of vulnerability. It wasn't until 2018 that someone put their hand up and gave a name and a logo to this type of bug. So thanks to SNCC, we now call this zip slip. But Bbot, as it rummages around the internet touching the target's hosts, it can download certain types of files. And if they're archives, it wants to look inside them to try to find more attack surface information. And importantly, it does this recursively. If you've got archives within archives within archives, it'll dig all the way through those layers, which looks like this. Bbot will extract an archive to disk. It'll then look at all the stuff in the top level of what it just extracted, and it'll loop back on itself so that anything that's an archive will itself get unpacked. And importantly, it does this as a sibling directory of the archive it's unpacking, and it does it to a name that's based on the name of the archive that it's unpacking. This means we can play with something called symbolic links, or symlinks, which are kind of like the Unix equivalent of a Windows shortcut file, but if it helps, you can think of them like the portals from the video game Portals. You know that game where whatever goes in one portal pops out the other one? Yeah, that one, Portals. So if you've got a symlink to like a regular file, operating on that symlink is like operating on the file that it points to. If you read the symlink, you read the file. Write to the symlink, you write the file. You can have symlinks to directories, and you can traverse into them, you can cd into them, or you can open a file through the symlink, and again, it's like a portal that takes you to another area of your own file system. And what's fun about symlinks is you can actually put them in many different types of archive files. And when someone extracts them, they spring back to life. So take Bbot. If we leave a malicious tar file on our website for it to scoop up, it will do so, and it will start to unpack it. So let's give it a tar file that contains a symlink and an embedded archive. The symlink will just point to the temporary directory as an example. The name of the tar file that's alongside it is going to match that symlink. So when it extracts that outer layer, it will create the symlink. And when it looks at the files it's just extracted, it will extract that tar file in a way that follows the symlink, and we can write something into the temporary directory in this case. But we can write stuff anywhere, as long as we've got the permissions to do it as the user extracting stuff. Now, this is like a bug class in and of itself. Arbitrary file write is valid in and of itself. With Bbot, it's possible to take it a little bit further, because the place where archive extraction happens is in the users /.bbot, which is very close to this tools directory, which is where Bbot keeps all of its third-party components like fuff and trufflehog. So we can count the number of steps up from that extraction location to get up to the .bbot and create a tar file with a symlink with the right number of /slashes, because you can have symlinks to relative file paths, including //. Give it an embedded tar file to extract in a way that will follow that symlink. And we can then put our own tar file in the tools directory. And what's novel about tools is Bbot adds it to its system path, so that any time Bbot wants to run an external command by name, Linux will look here first. And we've just put a malicious tar binary or executable in there. So the next time Bbot goes to extract a tar file, it will run our payload, and we can give it one. We can put a tar file inside this structure so that there's reason to run it straight away. It's kind of like a free toy in your cereal. But in this case, it's free shells on the machine of the person who's using Bbot to scan you. So that's one way that the unarchiving function was dangerous. There was another one I thought was quite cute, which didn't depend on that recursive behavior. So if we look at how Bbot normally works, we've got a website with a tar file on it. It's the HTTPX module that shows up for a look, grabs the HTML, and passes it along a chain of modules. So we've got our friend unarchive at the end, but right before him, we've got file download. File download is responsible for saving stuff to disk, and he's kind of curious. He's curious in the way that he saves things. He picks a file name that involves the lowercasing of the original file's file name. So if we include two files on our website that differ only by case, file download will download the first one. And as long as the second download happens within the same second, because the date stamp is part of the file name as well, the second download will overwrite the first one. And importantly, file download will raise two different file download or file system events. And unarchive now gets the job of extracting the same tar file to the same location twice. It's kind of similar to the previous case, but I think of it like a double extraction primitive. Single tar file extracted to the same place twice. And I thought, what can we do with this? So I noodled on it for a bit and experimented with various different tar file structures, tar files in tar files with symlinks and whatnot. And this was pretty close to what I wanted. The tar file with a symlink, and then it doesn't have the directory entry, but it's just got the plain old file with the file name of my symlink/tar. And importantly, the symlink comes first. And here's what GNU-tar does when it handles this archive twice. So we'll do the first extraction first. GNU-tar gets really nervous about extracting symlinks. It's happy to follow a symlink if one already exists in the place that stuff's getting unpacked to, but it doesn't want to lay its own trap. It doesn't want to put down a symlink and then accidentally follow it, because then you'd have a self-contained zip slip in tar. So instead, it drops a placeholder, just like a 0-byte file, and it adds to its to-do list to come back at the end and create the symlinks last. Moves on to the second entry in the tar file, and it gets mad because it can't do anything about it because there's something in the way, so it skips it and says, job done. I'll fix up those symlinks and call this first extraction good. Now we've got a symlink that maybe the second extraction could follow. Second extraction happens. GNU-tar once again gets nervous about extracting a symlink, and it gets mad that it can't put down its placeholder file. It gets so mad about it that it deletes the symlink we've just put there so it can create its placeholder, which sucks for us. We're in a loop now. We're not getting anywhere fast. What ended up working for me on my machine was to put that symlink in a read-only directory, because you can set the permissions on files within tar files. What this would mean is that point at which GNU-tar would normally get so mad and want to delete our symlink so it can put down a placeholder, it couldn't, because the directory within which the symlink was read-only. So this read-only directory is kind of like a protective cover for our symlink. It means that it's going to survive until the part where the file that would follow the symlink gets extracted. So this worked for me on my machine. Turns out, though, this doesn't work if tar is running as root, because root kind of doesn't care about not being allowed to delete stuff in read-only directories. It does what it wants, which was a pain for me because I reported both these cases to the maintainer of bbot. The first one popped off for them, but this second one wouldn't, and it took us 5 ever to figure out why. Turns out it's because they were running bbot in the official Docker image, which runs bbot as root, and so root would not fall for this trick. Took us a long time to figure it out. So bbot, what it now does is it creates a fresh, empty directory for every extraction, which is good practice when extracting any archives to make sure there's no surprise symlinks that could be followed. Now I want to talk about something called Git repo pillaging. While I was preparing for this talk, I realized this should be a talk in and of itself. There's a lot here, because it's all based on some work I did back in 2022. I wrote an obnoxiously long text file all about Git internals, and it's worth a read if you've got a couple of hours. I'm going to try and speedrun this section rather than leave it out. This could go really well or really embarrassingly, so please wish me luck. So this section's all about Git. Git is the distributed version control system. Most people know about Git through things like GitHub, but they know about things like clone, commit, and if they're feeling spicy, push. Maybe some people have looked inside the .git directory once they've cloned something off GitHub. They may look at it and think, that looks scary, and I think the reason for that is because it is scary. People may think that when you do a git push or a git pull, you're copying this .git directory wholesale back and forth between you and the remote. That's not what happens because what's inside .git is scary. I think I'm off by a slide, am I? Yeah. Hope it hasn't been like that the whole time. Running Git against someone else's .git is like using someone else's toothbrush. It makes people say, what are you doing and how'd you get in my bathroom? Instead, your Git client has a conversation with the Git remote where it discusses what's getting transferred back and forth so that your Git can stay in control of what's inside its .git to keep itself safe. Because there's things inside a .git that can hurt you because what's inside there is scary. Hooks, index, and config. Git keeps itself safe with regards to hooks by just not downloading them from the remote. We're not going to talk about hooks today because it's not exploitable in the case of Bbot because hooks have to be executable for them to actually run, and we can't make stuff executable when it gets downloaded by Bbot through the Git dumper module. Instead, we'll talk about index. The way that Git keeps itself safe with regards to index is it doesn't download it from the remote, instead it constructs it locally. The conversation that your Git client has with the Git remote transfers back and forth what's called objects. These objects get saved inside your .git directory, inside the objects directory. What's inside the objects directory gets used to build the index. Now, the index is kind of like a cache, and Git uses it so it can go fast. Git is nervous about certain types of files that may appear inside a Git repository, things like .. for obvious reasons, but also files named .git/ because then the checkout could put stuff inside your .git, which would be bad because what's inside there is scary. So Git gets nervous while building the index, and while building the index, it lets in normal-looking files but rejects stuff that looks sus. After building the index locally, Git then does a checkout, and it can produce your working directory based on what's inside the index because it's a cache. And it can do so naively because it knows it built it itself. Well, it thinks it built it itself. And it won't double check the entries in this file because it knows it built it and it wants to go fast because this file is supposed to act like a cache. Git wants to go fast, and if it had to double check this file and doubt itself, it would make it go slow. So what does the index look like? Let's add a file into it and then commit it. We'll call it hello world. We'll look in the index. We can see that the file name is inside the index file. We'll then add and commit a file called ZZA, a whole bunch of those, temp/houdini.txt. We'll look at the index. We can see that the file is listed in the index. We'll use ZZA find and replace to change ZZA to .. which now looks like this. It's got a whole lot of .. slashes in it, which is one of my favorite sequences of characters. Right up there with I love you and I'm proud of you. In that order. We can see we don't have Houdini in the temp directory, but if we do a git checkout based on that cooked index file, we will have one. So if someone runs git checkout against your evil .git directory with an evil index, you have an arbitrary file write primitive. Enter Bbot. Bbot has a module called git dumper. Git dumper recursively downloads exposed .git directories and does a checkout. Putting .git directories on your web server was very popular when people made web apps using the personal homepage language. Some people would do a git clone straight into their web root to deploy something. It's a fast way to deploy stuff and a bad way to deploy stuff. If someone downloads your .git, they can steal your source codes, secrets, and maybe they can find stuff to inform Bbot for more attack surface. There's a module inside Bbot called git, which when it sees a URL will ask the web server, do you have a .git? If the web server is like, yep, git tells git dumper, go get it. Git dumper also gets the index file. Git dumper does a checkout, which gives us our arbitrary file write primitive. We can use the old trick of that tools directory and overwrite the truffle hog binary, which gets run after the git checkout happens. And so if someone scans us with Bbot, we can get a shell through the git index file. That is the git index vector. Oh, we are not done yet. Git config. The way that Git keeps itself with regards to git config is it doesn't download it from the remote. Instead, the user stays in control of the config so that they can keep Git safe. If you look inside what's in the config file, it doesn't look that scary. But a few years ago, I read the documentation for what can go in this file, and some of those things do look scary. One of those things is the fsmonitor directive, which you can see is all about making the git index faster. So it's kind of like a cache for your cache. If you keep reading the documentation, you can see it could be a command to integrate with the fsmonitor daemon. I like the sound of specifying commands. If we specify a payload as the fsmonitor, the file becomes scary. It will then execute that command upon git status, add, commit, checkout, and probably other things as well. Enter git dumper. When git dumper does that recursive download of .git, then does a checkout, it'll grab the entire .git, which is very scary, and it'll grab a scary config file, maybe. And if we've put a payload in there, we can get shells, except we can't get shells. Because git dumper was sanitizing what it downloaded in terms of the config file. In particular, it would sanitize out the fsmonitor stuff. I looked at it for a while and figured out if you just move that up to the core line, it looks like a weird config file, but Git still parses it and it breaks the regex, and so we can get shells again. I wasn't the first person to find this though, because this code looks like it was borrowed from the Git dumper project, which rang a bell. It's one of the projects I believe back in 2022. I reported there was a arbitrary file write and RCE in it, and they didn't fix the RCE, they fixed the file write, I think, but they added a disclaimer to their README saying, don't use this, it's vulnerable. That warning is still there today. But last year, someone actually did try to fix the code exec through the config file, committed that sanitization regex. On the pull request thread about that, after it got merged, someone said this doesn't work for a few reasons. One of them being the trick I found where you move it up to the call line. The other one being that you didn't need to do that, you could leave it where it was because the regex was just that broken because regexes are hard. So I call this kind of like a source code supply chain problem. We normally think about the supply chain in terms of libraries and dependencies and things like that, or maybe in terms of our vendors in our vendor security program. But it's kind of like the idea of borrowing vibes and ideas from other people's project, and you kind of have vulnerabilities proliferate in that way, maybe. I don't know. Anyway, you can get shells on Bbot. That's the Git config. There's other cool stuff you can do with Git. You can have things like OMIZ shell, which puts the current branch name and status in your shell prompt. Run Git every time you cd into somewhere. So if you cd into a malicious Git repo, which you can't really convey via Git clone, then if someone unpacks a tarball that has a Git repository in it that's malicious, you can get code exec as soon as they cd into it. There's another trick to do with buried bare repositories as well, which is where you put a bare repo in a regular repo, which you can commit and push to GitHub. When someone clones it, if they run git status in the root, it's fine, but if they run it from a child directory, it will actually run arbitrary code. Same thing with add, commit, checkout, and probably others. And you can combine these tricks so you can have a repo that can be cloned, and if an OMIZ shell uses CDs into a child directory of it that has the bare repo in it, then arbitrary code runs. I wrote a huge document a few years ago. If you want to read more about this, I suggest you do. Thank you. That was hard. There's subtlety to this. Before you go ragging on Git for things like the FS monitor vulnerability or the index vulnerability, the threat model of Git is quite complicated, and I tried to reason about it in that document. So just before you go talking shit on Git, make sure you read the file, and then you can come to your own decision about whether these are useful features or vulnerabilities or bugs or whatnot, and whose fault it is really, whether it's Git or whether it's tools that integrate with Git. It's complex. Lastly, I want to talk about API key leakage. This section is a lot more straightforward and simple than the previous one. Sorry, that was me self-soothing, but it's a lot more simple. A user of Bbot can configure their Bbot with API keys. And these API keys then allow Bbot to do more effective and efficient attack surface mapping. So a user is almost incentivized to chuck in as many as they can for things like virus total, if you've got virus total money, or for things like passive DNS services, if you have access to that. And I want to talk about two of the keys in there that can be used by two different modules. We've got the GitLab key used by the GitLab module and the GitHub key used by the Git clone module. So I'll start with GitLab. So Bbot can interrogate repositories and user information from gitlab.com. It's kind of like github.com, but different. And when it goes to do that, if an API key has been configured within Bbot for GitLab, the module will send it up to gitlab.com. It gets complicated though, because you can run GitLab on-premise as well. Like GitLab, you can download it and run it yourself, which begs the question, where should the key go if a user has configured a GitLab key? Turns out it goes to both. So if a user has configured a GitLab key, this has been changed now, had configured a GitLab key, then we can cosplay as a GitLab server just by sending back the header that makes us look like we're GitLab. And when we get scanned by Bbot, it will send the user's GitLab key to us. See, I told you it was a lot simpler. The Git clone module uses the GitHub API key if it's been configured. And it does this by, whenever it has to clone anything from anywhere, it opportunistically replaces basically github.com in the clone URL with a version that has the user's API key baked in as part of the basic auth, which is great when a github.com thing is being cloned. It decorates that with the user's API key. It's not so great when it's github.com.attacker.com. That ain't github.com. So again, we can cosplay as GitLab and present a repository that will be cloned by the git clone module, which has a URL of github.com.attacker.example. I think I used in my lab. And when Bbot stumbles across this GitLab, it'll try and clone the Git repository, and then the GitHub key will be leaked to us. So those are the three stories I wanted to share with you today. I hope you enjoyed them. We went through the archive extraction or zip slip. We very quickly went through Git repo pillaging, and we've just gone through the API key leakage. So with Bbot, the way that users use it doesn't typically run all the modules at once. There are kind of these presets or packages of modules that a user can choose to run. They can run the kitchen sink preset, which is every module, but that's a lot. Users will typically pick and choose, and so not all the bugs we talked about today will be exploitable in all cases, or would have been exploitable in all cases. But for example, the unarchived stuff gets lit up by the web basic package, and I think the other web presets as well, and the Git stuff and the API keys gets lit up by the code enum preset. Just to kind of qualify who this could have affected. So I found these bugs earlier this year, and I wanted to get them fixed. I love this video. I want to watch it again. Yeah, we got time. So the Techromancer is the maintainer of Bbot, as I said. He's with us today. It was a pleasure to get to meet him the other night. He works at Blackland Security. It's a Blackland security project. So I hit him up early this year and dumped a bunch of pox on him, and he was an absolute delight to work with. We got to collaborate on some private forks. Like, shout outs to the GitHub security tab. Like, to be able to collaborate on a private fork is just awesome. So these have all been patched now, and it was just a delightful disclosure process. And a month ago, the Techromancer published this blog post, which is just an absolute class act blog post. Because I know this would have been difficult as a security consultancy to have someone turn up and say, there's vulnerabilities in something you've put out there. And this post is just so graceful. It's the blog post I want to model when this happens to Tanto Security. Because it will happen to Tanto Security. Because hacker tools can have bugs too. One day we'll put some code out into the world that will have a bug in it. And I want to model the kind of maturity that Blackland Security showed for this. Taylor Swift said, "I'll stare directly at the sun, but never in the mirror." As professionals, we have the responsibility to stay aware and stay frosty. Our tools can have bugs too. The way that we perform our jobs can have risk, and we are an important element in our clients' security posture, and that's why we're all here. And so practice things like segmentation and isolation in your job. Don't run that dodgy exploit off of GitHub or exploit DB on your host. Have a look at the code, make sure it's not going to hurt the thing you're pointing it at, but then run it in a VM or a container. Like, don't run stuff on your very valuable, precious host. And protect your customers' data. Protect their pen test reports. Like, these are very critical documents. Don't let the confidentiality of your pen test report depend upon the correctness of the code that you run. I'm looking forward to publishing a blog post on this. I spent all of my time making slides, but I promise it's going to be out in the next couple of weeks. In the meantime, we've got a rich back catalogue, and if you check out our blog, I hope you enjoy what's there. Go forth, find some bugs in hacker tools. You're a hacker, and there's bugs in our tools too. Maybe you don't feel comfortable contributing code to your favorite projects, but maybe you can find bugs in it, do high-quality vulnerability reports, get some bugs killed, keep your colleagues safe, keep your peers safe, and give someone who hunts pen testers a really bad day. Thank you very much.